Welcome back, everybody. A little thinner today, assuming people are getting sick a little bit. The whole thing, tryptophan poisoning and all that. It's deadly this time of year. Okay. Well, regardless, this is it's a damn shame. I try every fall. I try to make sure that I find some way to force all of the important material to not apply on this week, but this semester's whatever reason it failed. Because this is a very, very important concept once we finish this one. So basically, we have learned nothing new. We had already tested upon this in exam three, which I will be handing back towards the end of the hour, or hour and 50. Uh, but the call it an hour just ended early. Yeah. I would love to. Would love to. Um, so basically, we're not learning much anything new. This is already what we were doing in Unit 3.7. It's finding the antiderivative of these things. So, and just like before, like you can add multiple constants. You can find the integral of each, like the antiderivative of each piece, and each time add a new constant. But at the end of the day, you don't need to because you could just combine them all as one global constant and just call it capital C. So the antiderivative of x to the fourth is 1/5 x to the fifth. Antiderivative of 3x squared would be 3x cubed over 3. So the 3's cancel. We get just minus x cubed. Then plus 7 halves x squared plus 2x plus a constant c. Nothing too surprising, and this is just meant to really kind of hammer home the power rule and all its glory. And same thing with this one, but you notice that you need to simplify first. There is a little bit we can simplify because we can't just find the antiderivative of the numerator and the antiderivative of the denominator and then divide. That doesn't work. That's not how it works. Just like with differentiation. Yes.
Sorry, I might have forgot. Does the indefinite integral just mean that that's the antiderivative?
That's correct.
Okay.
That's what it means. The integral without any bounds is called an indefinite integral, and all it means is find the antiderivative of the integrand, the thing on the inside between the integral symbol and the dx, the differential. So this one, you can just simplify it first. And so that will become the integral of 4b cubed plus 2b squared plus 3. I'm going to write something and mention that it's a mistake to do so. You might be tempted to write this as 3b to the negative 1. And let's go ahead and do that because it's going to be 1. Like you're going to do 3b divided by b squared. That's b to the first over b squared. Top minus bottom in terms of the exponents. You get 3b to the negative 1. And then the last one would just be 1 over b squared, which is b to the negative 2, db. Now, I did this problem for two reasons. First reason is to show you that sometimes with integrals, it is better to simplify before doing anything else. We will learn next week, we will learn about integral substitution, and it is one of the most powerful tools that you can use. However, not everything needs a grenade. Not everything, like not every problem you face needs a gun. Sometimes you just need a knife for a knife fight. You don't need to bring extra machinery for something that doesn't need it. So sometimes simplification is enough. The other reason why I made this problem is to mention the stark contrast between the last two pieces. With the last one, when we do 1 divided by b squared, it makes sense to write it as b to the negative 2. Why does it not make sense to write it here? What is 3 times b to the negative 1? With a positive exponent. That's 3 over b. I see so many students want to write 3b to the 0 divided by 0, right? Because that's what the power rule says. It's The integral, the antiderivative of b to the a is b to the a plus 1 over a plus 1. So negative 1 plus 1 is b to the 0. Negative 1 plus 1 is 0. But that doesn't work, right? That doesn't make any sense. You can't divide by 0. It doesn't work. That's going to be a natural log of the absolute value of b. So in one context, it's better to look at it with a negative exponent, the b to the negative 2. Whereas in other ones, it becomes counter, like it actually works against you. So mathematics is all about kind of looking for those nuances and making like and questioning what you see. So that's why I wanted to do this problem. Now that we've simplified it, we can actually find an integral of it. So 4b cubed, antiderivative of that would just be b to the 4th plus 2/3 b cubed plus 3 natural log of the absolute value of b plus b to the negative 1 over negative 1 plus a constant c. Now I'm going to rewrite it more pretty, the last term, the b to the negative 1 over negative 1. But on an exam, in a time crunch, leave it as is, right? My rule of thumb is you don't need to simplify unless you're going to use it for something. We're not being asked to find anything about this, so we're done. So we get b to the 4th plus 2/3 b cubed plus 3 natural log of b minus 1 over b plus c. I'll go ahead and even box both of them and say that both are acceptable. Important to know that negative b to the negative 1 over negative 1 is 1 minus 1 over b, but still comfortable flipping between the two. Any questions on that? Yes, JT.
Sorry, the correct conversion, 3b negative 1 power, it's just 3b, 3 over b.
Yeah, that would be the better way to look at it, to realize immediately that you're dealing with the antiderivative of a natural law.
Okay.
Any other questions? Bless you. Okay, so this next one, I'd like us to do it together, and then I want you guys to do part B by yourselves. So once again, just like before, the problem is we cannot take the integral of the two pieces in the product and then multiply their integrals. We have to simplify first. We must simplify. Many students, especially once we get to 4.5 and 4.6, will want to look at this and say, oh, u is equal to 1 plus 3t. You don't need to do that. Unnecessary work. This one is just as simple as it looks. You just need to distribute the 1/3. The t to the 1/3, that is. And we'll get the antiderivative, the indefinite integral rather now, of t to the 1/3 plus 3t to the 4/3 dt. And just like with differentiation, we learned the little tricks that happen. We got really good at adding one or subtracting one from our fractions. Now we're going to get really good at adding one to our fractions, which is the same thing as just adding, in this case, 3 over 3. If it was 1/5, you'd add 5 over 5. If it was 1/7, you'd add 7 over 7, and so on and so forth. So this becomes t to the 4/3 divided by 4/3. I write it like this because we got to remember we're dividing by a fraction. So we're going to flip and multiply. And then the next one is plus 3 times t to the 7/3 divided by 7/3 plus a constant c, which we can then write as 3/4 t to the 4/3 plus 9/7 t to the 7/3 plus a constant c. By the way, fun little nifty fact about antiderivatives, and now something that you will now know about derivatives and integrals, is now we can check our work, actually. It's easier to check your work for finding checking to see that you got the right integral. Finding the right antiderivative can be a little more challenging, especially once you've got, like, if you leave it in unsimplified form. But one of the things I really like about antiderivatives is you could take the derivative and make sure you get back the integrand. If you take the derivative of this, you get t to the 1/3. If you take the derivative of this, the 7's cancel. 9 divided by 3 is 3. And 7/3 minus 1 is 4/3. You can check your work now. So that is a great thing. Additionally, once we get to 4.4, I will show you a nifty little trick to verify an integral for the most part. There's something you can do, and we'll talk about it when we get there. So this next one, make sure you're able to convert between radical and exponential form. That will be very, very important on this one right here. People watch the recording, you should pause it and work through this one yourselves. Here is the nifty little trick in case you've forgotten it, that the nth root of x to the m equals x to the m divided by n. Roots below, powers above. All right, I'm going to pause it now. Does it work? The answers up here. The first thing is converting the square root of x to x to the 1/2. The 1/2 times the third root of x to the 4th to 1/2 x to the negative 4/3. And then the 7/1 plus x squared, we can't really do anything with that. We kind of have to leave it as is. So that's two power rules, and then the antiderivative of an inverse trig function, and then adding 1 to them. So 1/2 plus 1 is 3/2. Negative 4/3 plus 1 is negative 1/3. And then flip and multiply to take care of the fractions. You get the final answer. Are there any questions? And you probably saw the pink thing. People watching the recording. We discussed that during the break for a brief moment. I'm just going to talk about it because one of the students was wondering, why does the power rule happen? So we knew what the power rule was for differentiation, right? We learned that one. And granted, we didn't go through a proof of it, but I could happily show you a proof at some point if you'd like to see it. It requires using the binomial theorem, if you remember that. Do you guys remember this? That x plus y to the n is equal to k equals 0 to n of nk x to the n, y to the n minus k. No. X to the k, y to the no. Oh God, what is it? It's k because you want no. Okay, n minus k, y to the k. You guys remember that thing? You all remember the binomial theorem? You guys remember what the end of the k, this little coefficient is? You guys remember it? Have you ever seen it before? If you haven't, no, okay, no worries. That's called the binomial coefficient. This is the binomial theorem. There's a multinomial theorem, which is awful. It has to do with multivariable stuff, but regardless, we did see the proof. We did see the theorem that was telling you that the power rule for differentiation is that the derivative, in this case, I'm choosing a plus 1 for a good reason, is the derivative of x to the a plus 1 would be a plus 1 times x to the a. So if you're trying to find out what the antiderivative, you have 1 over a plus 1 times the derivative of x to the a plus 1 is equal to x to the a. So it's kind of a weird thing, but if you're trying to figure out what would the antiderivative of x to the a be, you have to think about what you'd need to take the derivative of to get x to the a, which is a plus 1. And then you need to counterbalance the fact that when you do differentiation, you multiply by the coefficient by the exponent. You have to divide by the new exponent with antiderivatives. So that is kind of the connection there. That's the reason why the power rule works. Proving it for integers, not too terrible. Like proving it for whole numbers is fine. Proving it for integers, harder. Proving it for rational numbers, even harder. Proving it for irrational numbers is the hardest. But regardless, that's where it lies. Any other questions? Okie dokie. So this one here, a pretty quick one. The antiderivative of u squared would be u cubed divided by 3. I don't know why I gave us this much room. And the antiderivative, what function do I need to take the derivative of to get secant squared? Derivative of secant is secant of x tangent of x. Derivative of tangent is secant squared. So it's going to be plus tangent of u. Plus a constant c. This one, however, now there is a way to do this one using integral substitution. You can do it. I wouldn't recommend it though. There's something easier. Does anybody recognize, like, there's something there that we might know? I know we're all great with our trig, so I know we can tell what this one's going to be. There's an important theorem. There's an important Pythagorean identity, maybe. What is 1 minus sine squared equal to? Cosine squared. Thank you. Oh, it's good to see it. Good to see it. This is sine of theta divided by cosine squared of theta, d theta. Now, from here, you could do it. You could definitely do an integral substitution to figure this one out, but it would be unnecessary. What is sine divided by cosine? Tangent. This is tangent of theta, secant of theta. Because you've got two cosines in the denominator, so you can split that up into a sine of theta over cosine theta times a 1 over cosine theta, which is secant theta. And that's not the way we typically see it, but it is the same thing as secant theta tangent theta. So this is equal to secant of theta plus a constant c. I bring this problem up because I want to mention something that's very, very strange about differentiation and integration. If you take the derivative of secant theta, you do not get back your original integrand. You need to use some trig identities to convert it to that format. The point being is that sometimes it's a limitation. You can check your work by taking the derivative, but it's not always perfect. There are certain things, especially once we incorporate integral substitution, where when you take the derivative, it doesn't look exactly the same. And that's just based on how we have to sometimes simplify things to make them work. But there will be ways to kind of combat that. Okay. Then we have these three. I'd like you guys to do part A and B, and then we'll come together for C. So I'm going to pause the recording, go ahead and start working through it. So these are the answers to the two of them. I mentioned during the pause that if possible, I would like you to get to the point. Why isn't the pen not working? Stylus is not working. There we go. Let's see. I would like you to get to the point where you can skip this middle step. But I did bring it up because I don't know if people were watching, like looking up towards me while I was figuring this out. I do not have my integrals of cosine, sine, cotangent, secant squared, cosecant squared, cosecant, cotangent squared, cosecant, cotangent. I don't have them memorized. I have the derivatives memorized. I have far more important things that I need to know about besides just figuring out, like mastering that one. I can let my brain deduce it. I can let my brain do that. That way I can know all the Paw Patrol members, right? In order in the song. Do I still remember it? Marshall, Rubble, Chase, Rocky, Zuma, Sky. Boom.
That's big.
So that's far more important information than remembering what the antiderivative of sine is. What I do every single time is I ask myself, what function do I need to take the derivative of to get sine? The derivative of cosine is negative sine, so I need to counterbalance it with an extra negative. That's how I figure that out. So t to the 22 sevenths, that becomes t to the 29 sevenths divided by 29 sevenths. T to the negative 1 is the same thing as 1 over t, so that's natural log of the absolute value of t. And then negative 3/2 sine t has an antiderivative of positive 3/2. Why did it become a sine t? I don't know. Why weren't you guys asking me? That should be a cosine. was testing you guys and you guys failed. Come on. We got to look out for these things. I'm not perfect. I still bite my cheek when I'm eating. Don't we all? Next one, e to the x divided by 5 is really just 1/5 e to the x. Just like with differentiation, remember, don't bother doing the quotient rule in that type of a situation. You don't need to. You can just treat that as a constant. Dividing by 1/5, divided by 5 is the same thing as multiplying by 1/5. And then the 11 over x to the 2 to the ninth root of x squared, that's 11x to the negative 2 ninths. And pi is just a constant. So the antiderivative of pi is pi x. And we get our answer. Are there any questions on those two? Okay. The last one I did want to mention because it just looks creepy at first, but it's not. B to the square root 29. It looks intimidating. Square root 29 is just a number. It's a number slightly larger than 5. This is just a power rule. This becomes b to the square root 29 plus 1 divided by square root 29 plus 1. That's all it is. And you could write it as 1 over square root 29 plus 1 times the quantity b to the square root 29 plus 1. You could do that. That's fine. But this is fine too. And I'm not interested in trying to rationalize the denominator. That's stupid. That's unnecessary work. You could better memorize the colors of all the Paw Patrol characters. Come on, everybody. Zuma, what color? Orange. Great, great. We all know that. I'm glad we know our Paw Patrol members. My son was really into it for a while. Thank God it's over. Thank God it is over. That was a rough part of my life. Anyways, plus 1/4. 1 over the square root of 1 minus b squared is sine inverse of b, or negative cosine inverse of b if you're feeling cheap. And the last one, b to the 99. 99 is just a number. So this is b to the 100 over 100 plus a constant c. And that's that. Any questions about that? So remember that radicals are numbers just like anything else. If you have b to the pi, the antiderivative of that would be b to the pi plus 1 over pi plus 1. It's just a number. Don't be afraid of it. Okay. Any questions? Last thing before we get on to the most important section of Unit 4 is remember that we have physics applications. Yay! Right? We learned that the derivative of the position function s of t is the velocity, and the derivative of velocity is the acceleration. So we have the backwards direction now that we have antiderivatives, or in this case, we're now going to call them indefinite integrals. So if you take the indefinite integral of the acceleration, you get the velocity. If you take the indefinite integral of the velocity, you get the position function. Sorry, 1 second, Parker. Okay, so the other thing though about this that I do want to mention is remember initial conditions. Why does it keep disconnecting? So remember initial conditions, which based on your guys' performance on the last page of the exam, I'm actually pretty impressed. I think you guys do remember your initial conditions, which is pretty awesome. There were 2 questions on the exam. We'll talk about it then while you're writing. I'm just going to gush about that while we're writing this down. You guys did really well on 2 of the questions that normally many students have had trouble with in the past. So pretty excited about that. So which question had the initial condition? The antiderivative problem on the last page, the one that had 2 options. It's been a while. It's been over. It's been a hot minute, so you might not remember it. But either way, suppose that the acceleration of a function is given by a of t equals sine t plus 6t. What is this object? I have no clue. I have no clue what object would follow that trajectory, but let's just say it exists. Given that the initial velocity is 5 feet per second and the object's starting position is 10 feet, find the position of the object after 3 seconds. Okay, so one thing that I want to kind of make us understand, it says find the position of the object after 3 seconds. We can look at that and realize what we're being asked to do. We want S of 3. We want the position of the thing after 3 seconds. But now we realize what's standing in our way from finding that answer. We were given A of t. Well, that's not a problem. We know that if we take the antiderivative of A of t, we get V of t. If you take the antiderivative of acceleration is velocity, and the antiderivative of velocity is position. So we just need to do that twice. So we'll first do the so we need to find antiderivatives. So V of t will equal the antiderivative or the indefinite integral of A of t dt. So that's going to be the indefinite integral of sine t plus 6t dt. Antiderivative of sine. What function do I need to take the derivative to get sine? Cosine or negative cosine? Negative cosine, because the derivative of cosine is negative sine. So you have to double negative it. So we get negative cosine of t plus 3t squared plus a constant c. But I can find c. We're given an initial condition on v. I'm going to underline that one. The initial velocity is 5 seconds. This tells me that v of 0 is equal to 5. So I can use that to find c. And I deliberately chose this problem to remind us that just because it's 0, it doesn't guarantee that c is equal to 5. You have to solve for it every time. A lot of times it ends up just going away. A lot of times it does, but that's not guaranteed. It's not it's not always correct that c is equal to that number. You have to test it each time. So v of 0 equals 5. That tells us that negative cosine of 0 plus c is equal to 5. That gives us negative 1 plus c is equal to 5, which gives us c is equal to 6. Any questions on that? So this one, we're given an initial condition on the derivative, and we're given an initial condition on the object's position. We're given that S of 0 is equal to 10. We know the starting position is 10 feet above whatever we're measuring. Above or to the right of us and to the left of us, depending on how we're measuring this whole object. So now we know what C is. So S of t is the antiderivative. It's the indefinite integral of V of t dt. So that's going to be the integral of negative cosine of t plus 3t squared plus 6 dt. And then we just need to take the antiderivative of that. We need to find the indefinite integral. Another way to say it is we need to integrate it. We need to find the indefinite integral of that quantity. Antiderivative of cosine of t is positive sine, so it's gonna be negative sine of t because of that extra negative sign, like that negative sign out front, plus t cubed plus 6t plus a new constant d. You can rename it c if you want, but it's convention to write as a new letter or to use subscripts. So C1, C2, C3, whatever it may be. Then we use S of 0 equals 10 to find D. That tells us that negative sine of 0 plus 0 plus 0 plus d is equal to 10, which gives us that d is equal to 10. Because sine of 0 is 0. Just as a reminder about what we're doing, we're writing this for notes so we understand where everything's coming from. But you don't need to write that the antiderivative of like S of t is equal to the antiderivative of v of t. That's just for our note-taking purposes. You can immediately go to this. S of t is equal to that. Hell, you can even go straight from here to here if you really want to. You don't have to show the indefinite integral. We know that it means the antiderivative. So that is okay. And we haven't finished the problem, though, because we need to find S of 3. So S of t can now be written as negative sine of t plus t cubed plus 6t plus 10. So S of 3 would be negative sine of 3. Make sure your function, your calculator is in radians because we're only dealing with radians in this course. Plus 3 cubed plus 6 times 3 plus 10, which is approximately, if you plug it into your calculator, 54.86 feet. Any questions on that? Good? That was quick. I do want to get to the next section. It's really cool. Coolest section. Okay. Going once. Going twice. Is anybody still writing? Yes. Alex.
Are there gonna be questions? Is this something you would like to test on the physics stuff, or is this just to demonstrate that this is how it connects back to physics and what we were learning earlier?
So I don't know, once again, what's on the final exam. So it could show up. I'm not too certain. It hasn't happened too often in the past, so I wouldn't be I'd be a little more surprised than normal, but it is fair game. It is an application. And sometimes they like to throw application problems. But seeing as this is the very end of the semester, they try to, and remember, a final exam is supposed to be an overview of the knowledge. I think they're going to be focusing, I guess, they're going to be focusing more on the fundamentals of Unit 4. Okay? All right. So, oh, wait, no, we don't need this. This isn't my other class. Unit 4.4, the fundamental theorem of calculus. You've probably heard that terminology before, the fundamental blank of blank, the fundamental theorem of algebra, the fundamental theorem of arithmetic, the fundamental theorem of probability, or what they usually call the fundamental counting principle. The reason why they're called fundamental is that they must do in order to be called a fundamental theorem, you must be so central to a concept in that thing that it becomes iconic. And so, it's been we've separated calculus into these 3 chunks: limits, differentiation, and applications, and then we're working on this new thing, integration. One of the things that was plaguing mathematicians at the time is, is there any connection between all these things? We know that the indefinite integral is the antiderivative, so that's connected to differentiation. But what about this definite integral? What's the connection to it? How does it relate? And that's where this comes into play. This was actually Newton's advisor was the one who I think discovered this. And then we've expanded upon it since then. But I believe that would, if memory serves correctly, that's what Newton's advisor at his college was working on, was the connection between differentiation and integration. So, in order to figure that out, though, I want you to consider a new function, the quote-unquote area function. Because once again, remember that an integral can represent the area under the curve, but it can also be negative because of how it's constructed. As a mathematical object, its heights of its rectangles can be positive or negative based on whether you're above or below the x-axis. So that's why I'm calling it the quote unquote area function and not an actual area function. Well, what you're going to do is you're going to call it a of x is equal to the integral from a to x of f of t dt. Which looks weird. It looks weird, right? Because we're used to seeing, like, for generic integrals, we're used to seeing it as the integral of f of x dx. Why is it t dt? Imagine if it were x as well. Then this would be a of x. So don't write this down. Let me write this in red instead. That would be a of x is equal to the integral from a to x of f of x dx. That doesn't make any sense because a differential is just talking about a variable in question. And if I'm using this, then when I plug in 1, a of 1 would equal the integral from a to 1 of f of 1 d1. Does that make any sense? No. That's talking about a number now. And you can't, like, f of 1 is a constant number. It's a constant. D of 1 doesn't even make any sense. So that's why it has to be a different variable. If you'd prefer, some textbooks might write it like this. If you don't like seeing your variable f of t, on your function being t, you could also write it as a of t is equal to the integral from a to t of f of x dx. It doesn't really matter. It really doesn't change anything. But it's better to think about it this way instead, because we need to think about this as the function. We're not interested in f so much as we are interested in a. A, what it does is it calculates the area, quote unquote, under the curve f of x for an integral from a to x. So this is an example of this. That first shaded region, I've got x sub 1. That shaded region, that is a of x sub 1. Whereas if I make it larger, that's a of x sub 2. So, in this context, from a, noticing that the function increases indefinitely on the right-hand side, is a constant function, an increasing function, or a decreasing function? Increasing mean that every single time you increase the increment, you move x over, does a of x get bigger? Yes, it does. Because each time you make x get a little bit larger, you're adding on a little more shaded region. You're adding more area each time, especially since this function increases indefinitely. If this function started to decrease, then at a certain point, we'd start adding negative areas, and then it would start decreasing in size. So there's a connection there that I want you to think about. This function can increase or decrease depending on what f of t is, depending on how f of x looks, depending on how everything shapes out to be. Now, this function by itself may look a little bit stupid. Like, it might look like its only application is figuring out the area on a certain segment, but I'll show you in a little bit that that's not true. This is an important function. So let f be a continuous function as we've seen below. It's not differentiable everywhere. It's got some corners and some cusps, but regardless. And define g of x to be the integral from 1 to x of f of t dt. So that's its quote unquote area function, starting at 1 and going onwards. Find g of 1, g of 6, and g of 9. It looks intimidating, but remember, all you're doing is you're plugging in 1 for what x is, or 6 for x. Not for t, not for dt, because those are different variables. So g of 1 is going to equal the integral from 1 to 1 of f of t dt. And what will that equal? You have to remember what the integral does. The integral adds up a bunch of rectangles between a and b. But here, a and b are the same number. So the delta x's in the definition would be 0. The width of every rectangle that you try and add will always be 0. So this thing is 0. There's no width. because of the fact, I mean, you could, if you'd like to, we can highlight the fact that they're the same bounds. The upper bound and lower bound are the exact same number. So if we were trying to add up the rectangles, there would be no width, meaning that there is no actual area, zero area. Then we're asking, and just as a note, the note was there so we didn't have to calculate things. A quarter circle, if you go from 7 to 9 on this graph, you have a quarter circle. It doesn't look like it, but on the exam, I would make sure that it looks very, very clear that it's a quarter circle, if that was the function shown. But just to save on time, that's a circle with radius 2. So a quarter of a circle with radius 2, the quarter of its area would be pi. Just as a useful tip. Just save on time. So g of 6 is the integral from 1 to 6 of f of t dt. So that is going to be this shaded region. Well, let's use a different color. Let's use green. That right there is g of 6. That's the area under the curve between 0, from 1 and 6. And once again, we all know our formulas for trapezoids, which I'm so glad that we know because it's a super important formula. I bust it out every day. I know we all do, right? Gabby, have you been using the trapezoid? Good. I'm certain of it. Right? It's 1/2 the base 1 plus base 2 times the height. So you could use that formula. If you don't remember that on an exam, please remember that you can always split this up into 3 pieces. 2 triangular pieces, 1 rectangular piece, and add them together. But I'm going to be, as the kids say, I'm going to be a Chad and recognize that this is going to be 1/2 base 1, which is 5, plus base 2, which is 2, times the height, which is 2. And that will be 7. So trapezoid formula, like a boss, as the other kids say. It feels weird to say that. I know that's probably 2000 late, but like a boss, you got that. So I guarantee you, though, once again, if you split it up into 3 pieces and add them together, the area of this triangle is 1. The area of this is 4. Sorry, 2. This is 4, and this has an area of 1. You're all done. You get 7 at the same time. Last one is g of 9. G of 9 would equal the integral from 1 to 9 of f of t dt. And so I'm going to write this one in dashed lines. And say that that's the whole area from 1 to 9. So you got the trapezoidal piece plus the negative area. Because remember, I'm not talking about area here. I'm talking about an integral. A definite integral can be positive. It can be negative. So if we're looking at this purely as a mathematical object, when we add the piece from 6 to 9, we're going to be adding negative pieces. Because on those pieces, the function starts having negative area. So this is going to equal the area of the trapezoid plus the area of the negative triangle plus the area of the negative quarter circle. Because don't get it twisted. So don't worry, I'll let you write that down. But it doesn't go completely vertically down. So it's not an actual quarter of a circle only. There's also that little tiny triangular piece. I'll illustrate in just a moment. So if you haven't finished, don't worry if you haven't finished. This right here is that triangular region. And then this is the quarter circle region. No, I don't want there. So that's going to be equal to the area of the trapezoid, which we found to be 7, plus negative 1/2 the base, which is 1 times the height, which is 2, plus negative pi. The first piece, the negative triangle, it's below the x-axis, so the height of it would be negative rectangles. That's why it's negative. And if you compute that, that's going to be -1. So 6 plus -1 plus negative pi equals 6 minus pi. So if you're thinking about the function g, it goes from increasing between 1 and 6, and then starts decreasing from 6 to 9. Think about that one more time. As I go from 1 to 6, I keep adding more and more and more area. So even though it kind of maxes out at 5, and then I start adding less and less area, I'm still increasing. I'm slowly leveling off. I'm slowly stopping my increase. And then at 6, I start adding negative area, more negative area, more negative area, more negative area. And then around like at 7, then it starts becoming less and less and less, but it's still decreasing. So it's a matter of looking at, like, if you were to look at the function g, it would have a relative maximum at 6. Because at 6, it goes from increasing to decreasing. And then it would have a relative minimum at 9, because it goes from decreasing back to increasing. Because now after 9, we start adding more area. Any questions on that? The whole point I'm trying to get at with this function is that it's a function. It has a shape. It has designs. It has important properties, just like any other function. And just like every other function we've seen before, we now know that there are derivatives. There are integrals of functions. There are many other things you can do with functions. We've learned them from 126 and before. You can transform a function. You can scale it. You can do so many things. You can compose functions. All of that stuff is possible. So we get to the fundamental theorem. Now, some textbooks will say that part 2 comes first. They will say that this one is part 1. And they're wrong. They're very, very wrong. Part 1, there's a reason why we call part 1. Even though part 1 is not nearly as important as part 2, part 2 is far more applicable for real life. That's why they usually argue that that should be part 1. But the fact of the matter, which we'll see on Wednesday, is that you need part 1 in order to prove part 2. That's why it should be organized that way. I'm very, very particular about that. That's the hill I'm willing to die on. So the fundamental theorem says, suppose that f is a continuous function on an interval a to b. Then, if g of x is that quote-unquote area function, so it's the integral from a to x of f of t dt, then the derivative of g is f of x. Written differently, the way that most people want to write it, and the way that makes it more clear what we're saying, is that g prime of x is equal to d dx of the integral from a to x f of t dt, which equals f of x. The big deal here, this was the thing that was plaguing mathematicians for a long time. This verifies that integration and differentiation are inverse operations of each other. Just like multiplication and division are inverse operations, just like addition and subtraction are inverse operations of each other, just like logarithms and exponentials are inverse operations of each other. We now know definitively that differentiation is the opposite of integration. If you integrate something and differentiate it, you get back to the starting point. That's the key. That was the thing. That's the reason why that was so central. It connects so many things, and we'll see in the proof why it connects so many things. It's very, very fun. Every teacher has one thing that they call their baby, and this is my baby. I showed this, and this is not the way it's traditionally proven in most textbooks because they're trying to use a lot of machinery that is beyond the scope of this course. I was trying to make it as relatable as possible to everything we've seen. So we're gonna have a grand old time on Wednesday doing that if you are going to be here. If you're sick for whatever reason, I understand, but you're missing out on something awesome. Okay. The far more important part. This is the thing that you will be using far more often in the rest of your calculus career. This one, important if you're going to become a math major. If you're not going to become a math major, you're probably going to use part two far more often. If f is any antiderivative of lowercase f, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. This is super useful. Instead, like as you saw in 4.1 and 4.2, in order to find the actual area under a curve, we had to first create a formula for the nth Riemann sum and then take the limit as n goes to infinity. That took a lot of time and a lot of work. But what we discovered is that if you have the antiderivative, all you need to do is plug in the endpoints of your interval, take the difference, and you find the area. That is super nice. That is a very, very useful fact. And we'll see that in a moment. Just to show an example of part one, g of x is equal to the integral from -10 to x of the square root of 100 minus t squared. Find g prime of x. Capital G prime is equal to d dx of the integral from -10 to x of the square root of 100 minus t squared dt. And that just becomes the square root of 100 minus x squared. The point being that if you take the derivative of an integral, you get back the integrand. The derivative and the integral undo each other, and they like, so some students, just like with limits and stuff, you kind of like go like this. I don't like doing that in this case because there's a little more nuance to it than that. If you decide to go really far into mathematics, you'll understand the nuance there. But for all the things we'll be seeing, that's mainly what it does. But we'll get to that sooner or later. Let's go ahead and take our first break. Well, our only break. Sorry, I just keep like my class right after you guys. They have two breaks because they're a 3-hour class. But yeah, let's come back at 10:10, and we'll pick up then. People watch the recording, do some guided meditation, and 10 push-ups. So that's an application of the first, the part one of the fundamental theorem of calculus, which, by the way, just to abbreviate, I realized I should mention, we always call this the FTOC. The FTOC. If there is one portion of it I want you to memorize, it's part two. That to find the area under a curve, quote unquote area under a curve, you do capital F of B minus capital F of A. It doesn't matter what the like which one's larger, A or B. It doesn't matter. It's always F of the top minus F of the bottom. F of the upper limit minus capital F of the upper limit minus capital F of the lower limit. So let's see how we write that. And once again, we'll be going over this on Wednesday. Yes, JT.
The capital F, what is, how can it becomes F?
It's the antiderivative.
Okay.
So in order to find the area under a curve, we find the antiderivative, and then we plug in the bounds and take the difference. So this is how we write it. So first and foremost, we need to know what the antiderivative of x cubed is, which is 1/4 x to the fourth, right? So this is equal to x to the fourth divided by 4. And this is the way we write it. Some people will write a vertical line. I prefer you write a giant bracket like that. And then you write the bounds here, 1 to 4. This this little bar, this bracket with the 1 and the 4, this means evaluated from 1 to 4. That's what it means. And so all we need to do then is to plug in the 4 into the antiderivative, x to the 4th over 4, then subtract 1 to the 4th over 4. So it equals 4 to the 4th divided by 4 minus 1 to the 4th divided by 4. That's 255 divided by 4. That's a lot faster than calculating the formula for the nth Riemann sum, wouldn't you agree? Way faster. So much nicer. And the great thing about my calculator that I've recommended to you is if you look on it, there should be a button that has a definite integral on it. So now you can check your work. Now remember, this is to check your work, not to replace your work. So on these problems, I will be making sure if there is one on the exam, which I would be shocked if there wasn't, there's going to be at least one definite integral in some way, somehow. I guarantee it. It's just an important part of Unit 4. I need to see you demonstrating the fundamental theorem of calculus, but there's nothing stopping you from checking your answer in your calculator. So it should work out. Did you get a different one? Do you get a different answer or no?
Checking.
So it usually gives it as a decimal approximation because if memory serves, they use Riemann sums to calculate these things. But there might be something new that they've started to do with calculators. But back in the day, that's what they would do. But 255 divided by 4 is 63.75. The integral of x raised to the third power from 1 to 4, 63.75. It worked out. So, did you get the same answer?
Can't find the buttons.
Okay. Let me know if you can't find it. Let me know. And I'm sorry, Kiana, you don't have the good calculator. It's okay though. You can still check your work by plugging it in. Okay. So, a couple things. First thing that I like, there's a question I want to ask is why didn't we use x to the 4th over 4 plus c? The most general antiderivative. Why didn't we use the most general antiderivative? We've been told since the beginning we should be using the most general antiderivative for these things. If I want to find the antiderivative, I'm usually talking about the most general antiderivative. Well, there's two reasons here. Reason one, it wouldn't matter. It wouldn't matter at all because you'd add c in the first place, and then when you do the subtraction, you'd be subtracting c. It would cancel each other out, but let's see that in action. X to the 4th divided by 4 plus a constant c, evaluated from 1 to 4. That becomes 4 to the 4th divided by 4 plus c minus 1 to the 4th divided by 4 plus c. And when I distribute it, the c's cancel. When I distribute that minus sign, the c's cancel. So that's one reason why you don't need to bother using x to the 4th plus x to the 4th divided by 4 plus c. It isn't needed. It'll just cancel out anyways. That is reason number one, but there's a more clever reason. So alternative reason. And the fact is, if you look back at the theorem, the fundamental theorem of calculus, it says if capital F is an antiderivative. So it doesn't matter which derivative you use. So any antiderivative, it'll always give the same result. whether or not you use a constant capital C, or if you use the one that has a constant of pi, or one that has constant of 1, every single time it's just going to cancel out. So it says any antiderivatives. So why not use the nicest one with C equal to 0? Smiley face. Being clever, saving yourself some time, saving yourself some carpal tunnel, because you're saving yourself 1, 2, 3, 4, 5, 6, 7, 8, 9. Set 9 pen strokes. You're just saving yourself. You don't have to do it. Make it the most, don't do the most general antiderivative, because the FTOC can work with any antiderivative. Okay. Any questions on that? Okay. This next one. So we're going to do these together, at least at the start, and then as we go along, we will move on. So this one, antiderivative of cosine. What function do you need to take the derivative of to get positive cosine? Positive sine. Derivative of sine is cosine. So this is equal to, we found the antiderivative, it's sine of u, and we're evaluating it from u equals pi over 4 to u equals pi over 2. And then all that is capital F, which in this case is sine of u. That's your antiderivative. Evaluated the top minus it evaluated the bottom. The upper limit minus the lower limit. So that's going to be sine of pi over 2 minus sine of pi over 4. Sine of pi over 2 is 1. That's good. Sine of pi over 4, square root 2 over 2. Good. I'm glad we're getting it all. I saw that on the exam, that we all knew our trig very, very well. I'm being a little sarcastic. We did pretty well. We did pretty well on our trig on that one problem, but I'd like to see better. And that's okay. Trig can be a little triggy, but it's okay. And so you can leave it like this, or you can write it in the more rationalized form. It's fine either way. I'd prefer this. Any questions on that? So you just calculated the area under the curve cosine between pi over 4 and pi over 2. Just as a small aside, if we want to look at this, just visualization, remember that cosine of x starts at 1, and here's pi over 2. Cosine goes like that. And so if I want to find the integral from pi over 4 to pi over 2, I'm asking to find the area of this region. All right. So it should be a positive number, and that's what it is. 1 minus square root 2 over 2 is a positive number. Not a very large number, but it's still a positive area. All right. Let's see here. Let's go ahead. I'd like you guys to work through these two yourselves. I'm going to slowly pause. I'm going to slowly fill in the details. All right. In all its glory for part A, we'll come back to part B in just a moment. But the thing is, once again, you need to simplify first. You need to make sure you take care of the division, because otherwise we can't find the antiderivative. So dividing x by x to the 1/3 gives me x to the 2/3. Dividing x squared, which is the same thing as 6/3 divided by x to the 1/3. Take away 1 of the thirds, you get 5/3. And don't forget about that too. So you have the integral from -8 to -1 of 1/2 x to the 2/3 minus 1/2 x to the 5/3. Integrating those, the 1/2 is constant, so you can ignore it, but then it's going to be x to the 5/3 over 5/3 minus 1/2 x to the 8/3 over 8/3, evaluated from -8 to -1. We were talking about during the break is the fact of the matter is it doesn't matter the bounds. Like, this is more left on the number line than -1, but even if it wasn't, even if I gave you the integral and I made it from -8 to -100, you would still do the upper limit minus the lower limit.
regardless of which number is bigger. It does not matter. It always works that way. Because remember, it's a mathematical object at the end of the day. We saw that we can, in fact, back in 4.2, where is it? Right here. We saw in part B that you can flip the bounds of integration, because what it does is it makes the widths of your rectangles negative. So it just makes, like, because now instead of doing b minus a divided by n, you're doing a minus b divided by n, making negative rectangles. It is allowable for that to happen. So it's always, though, it's always upper limit minus lower limit. Capital F of the upper limit minus capital F of the lower limit. So back to the point. Simplifying it a little bit before I have to do the calculation. 1/2 times 3/5, because you flip and multiply, you get 3/10. 1/2 times 3/8 gives me 3/16. And then I plug it in. This portion right here, the last calculation, worth about 1 to 2 points at total on a problem. If it's a 5-point problem, it's only probably going to be worth 1 point. If it's a 10-point problem, maybe worth 2. Depends on the Seahawks, right? This is the big step I want to see. I want to see that you understand what the fundamental theorem of calculus does. We take the antiderivative, we plug in the upper bound, subtract the evaluated the lower bound. If you show me that, that's a guarantee, and this is correct. Like, you've plugged in the numbers like properly in for x's or whatever the variable is. That is an 80% at least on that problem. Now, as a small aside, if you want to, because remember that the antiderivative of a product, or sorry, as of a sum or a difference, is the sum or difference of the antiderivatives. If you'd prefer, you can instead just find each one separately. You can find the integral, like the piece from 3/10 of x to the 5/3, evaluated from -8 to from -1 to -8, minus 3/6 8 to the 8/3, evaluated from -8 to 1, or -1 to 8, depending on how you want to read it. And you can do it that way. So you can do this piece and this piece separately. It makes it look a little more relatable, like all the pieces are the same. So it can be helpful to view it that way. But since we have calculators, we can do this much faster. And that's another thing I wanted to mention. Use your calculator for this. Lord help you. Like, that's unnecessary brain space. Once again, you'd be much better off knowing what each Paw Patrol character rides, right? Rocky, what does he use? A garbage truck. Very, very good. Don't lose it, reuse it. Yeah. You can also memorize the catchphrases. Next one. Antiderivative of e to the theta is itself, because that's the only function whose derivative and antiderivative are the same. As we continue on, you'll see why e is a much cooler number than pi. So once you've taken calculus and beyond, you start to realize that pi day has nothing on e day, because he is just so much cooler. Antiderivative of secant squared is tangent. So we have e theta, e to the theta minus tangent theta, evaluated from 0 to pi over 4. Plug in pi over 4, the top bound minus the lower bound. Tangent of pi over 4 is 1. There we go. And we totally didn't use our calculator to figure that out. Excellent. E to the 0. For all my students, geography for 126 is 1. And tangent of 0 is 0. So at the end of the day, if you want to simplify this, this is e to the pi over 4 minus 2. So, any questions on that? We're going to skip the generalization. We're going to talk about that on Wednesday, because it's not as important as the rest of the stuff. I want to talk about the definite integrals and areas under the curve, because now we have a much faster way to do it. We are able to find one, like, first and foremost, we're able to find it quicker, even with the things that we were able to calculate. But now we can even do it with things that we couldn't calculate, because there's not a nice formula for summations involving a square root. Maybe there is, maybe there's a formula out there, but I don't know it off the top of my head, and I wouldn't expect you to know it off the top of your head. That's the thing that mathematicians who are really bored might do. So, use definite integrals to represent the area of the region bounded by the curves y equals 2 plus the square root of x, y equals 0, x equals 1, and x equals 9. Then compute that integral or integrals. So Context is needed here. This is saying the area of the region. I'm talking about an actual area now. I want a positive number. So if my curve ends up being below the x-axis, I need to tack on negative signs to account for that. So it depends on the context. Here it's not saying evaluate this definite integral, because a definite integral by itself with no context can be positive or negative. But here I want actual area. So first and foremost, let's graph what this looks like on the side. The square root function typically looks like that. But this has been shifted up 2 units because it's 2 plus. So it kind of looks like this. Here's 2. And there's y. But I want to understand what it's saying. It's bounded by this curve. So by itself, one curve bounded where? Bounded above, bounded below? Am I talking about this region or am I talking about this region? The purple or the pink? That's a good question. I need more context. I also say it's bounded by the curve y equals 0. Y equals 0 is this curve. This is y equals 2 plus square root x. And then it says x equals 1 and x equals 9. Those are vertical lines, one at 1, one at 9. Here is 1. Here is 9. This is x equals 1. And then we'll do the same thing for 9. X equals 9. So we're talking about this region in particular. This region, which I'm going to call capital R. So this region is already above the x-axis. So the integral and the definite integral and the actual area will coincide. So we can even write that here. Because above x-axis, the integral and actual area coincide. How do you spell coincide? I know the actual area are the same. I swear I know how English works. I just don't remember. I think it has, is it coincide with a C or is it inside with an S?
With the C.
Well, whatever. So when we calculate this, we don't need to do any worrying about adding on an extra negative. So the area of the region, A sub r, will equal the integral. The x1s here give us the bounds because remember, this is a dx integral. Now, if you plan on taking 182, you don't need to draw this yet. But in 182, we'll start drawing a vertical line and call that dx to remind us that we are adding vertical rectangles. We are adding each rectangle having a width of determined by x. But what's really cool, in 182, you actually start asking, what about this? Could you add them up based on y? Good question. That's for 182 for us to figure out, though. The answer is no. No, I'm kidding. The answer is definitely yes. It's pretty cool. But we'll get there. So the bounds here are 1 and 9. And then the function in question is 2 plus the square root x. We're trying to find the area of the rectangles that get formed by using 2 plus the square root x to determine the height. So this is going to be the integral from 2 plus the square root of x dx, which, remember that square root x can be rewritten as x to the 1/2. So that will equal 2x plus x to the 3/2 divided by 3/2 evaluated from 1 to 9. That one. Oh, that's a fun question. All right. Sadly, we won't get to it because we're gonna after this one we're gonna stop and we're gonna talk about evaluations and the exam. So then this will be 2 times 9 plus 2/3 times 9 to the 3 halves minus in parentheses, bigger parentheses, 2 times 1 plus 2/3 times 1 to the 3 halves. And that will equal 100/3. So this is how we were able to create the we are now able to verify formulas of different area formulas that we've learned. If you want to, oh no, you can't do it yet. You need Calc 2. But there's a way to derive the formula for the area of a circle. It's pretty cool. Or the area or the volume of a sphere. But those we'll get to those. Let's go ahead and pass these out. I'm gonna pause it real quick because this is where we'll stop for today. All right, so I just handed them back. I just want to really commend you guys on question 7. You guys killed it. There was a typo on it. Questions part B and C were supposed to be worth 2 points. Otherwise, it was worth 12 and 12, which was not correct. It was only worth 10 points. But questions B and C and D, I was really impressed overall with you guys' performance on that. That was pretty cool. And then it's supposed to be question 9, but it says question 1, doesn't it? On the last problem.
Yeah.
Oops, typo. No worries. That one was also really great. What are we thinking? Are we thinking we want some extra credit for doing the other option?
That review's gonna look really.
Makia, no? That means no, right? Okay, that means yes. Okay. Let's go with 2 points or 3.
Let's put Christmas present.
3. 4. How about that? Fine. Double it. I'm with it. 4. Good job advocating for yourselves. You always want to advocate for yourself. No one else is going to do it. When you get into a job, demand that salary bonus. If they say no, that's fine. Find another job. Right? Okay. The other thing before we make sure so you have until next Monday. That being said, that's Thanksgiving this weekend. Let's go Wednesday. Turn it in on Wednesday, okay? Spend more time with your family than you can if you can. So if you want to turn it in on Monday of next week, feel free to, but you have until Wednesday. Let's have a little bit of grace. The other thing I want to talk about. So yes, you can do the extra problem on the last problem on the exam. You can do that one for an extra 4 points, up to 4 points. So evaluations are starting to show up in your mailbox. I want to mention that I have no control over how obnoxious it becomes. If you've never taken an evaluation, if you've never done an evaluation at CSN with Canvas, what it will do is it will eventually be really obnoxious. It'll start saying, like, you'll click on something and say, hey, you haven't done your evaluations. And you'll say delay, and then you'll click on a new link on your Canvas page, and they'll say, hey, you haven't done your evaluations. I have no control over that. I've asked OTS about it before to like if I could disable it, and there's no way to disable it because I know that's annoying. That being said, what I would like you guys to do, if you have the time, please fill those out, not just for my class, but for all of your classes. A couple things to know about it. It's anonymous, and especially since it's a math class, I have no clue what your regular writing is. I don't get to see your guys' typical writing style. I just see your math writing style. So there's no way for me to know who's who anyways. But even still, these things do not get sent to us until after the semester is over. So there is no worry. I hope we've established enough of a rapport that you know that I would never do that. But if you're worried, like if you have a professor that you dislike and you want to rail into them for something, there is nothing they can do. Grades will already be entered. Even if they were to somehow, like maybe they kidnap our OTS director and have them look through the code and figure out which student's which, there is no way for them to do anything of ramifications. You can give your completely honest critiques. So please do so, even if they're negative, because that's the only way we can become better as teachers. And even like, and you might be thinking that it would be fruitless. Maybe you do have a teacher who you don't think will even bother to read it, and that might be true. Every teacher is supposed to read these things. I look forward to reading them when I get them because I look forward to seeing what you guys have to say and what you guys think should be approved upon and or kept. But there might be some teachers who don't. But guess who will look at them? Their department chairs will definitely look at them. So if nobody speaks up about a bad instructor, even if that's me, if nobody speaks up about it, then nothing happens. But if you do, if enough people show up on their evaluations, that shows up enough on their evaluations, their department chair will look into it because every year we do have our own meeting with our department chairs about our performance. So, and your department chair is supposed to look through your evaluations to make sure everything's going according to plan. So you do have power here. I would really like you to be critical of the course. Tell me what you liked, what you did like. As much as I love the comments like Phil, you rocked, or Phil, you sucked, major ass, right? What did I do that rocked? What did I do that sucked, said major ass, right? What is the problem? What is the problem? Was I too hilarious? Was I too great of a teacher? Was I too humble of a teacher? Was that the problem, right? I'm very, very interested in those types of things. If there's things that you think could be improved upon, please let me know. If you think that we like even if it's something like I can handle it. My only request is that you be like, considering that consider that I am a person. Like don't like be very, very mean. Be poignant, but don't be mean, please. I have feelings, but I can handle it even if you do dislike me a lot. I can handle that. I'm okay with it. But I would like to know your honest critiques. So anyways, I think I've hit all the main bullet points. We don't see it until after the semester's over, after grades have been inputted into my CSN, have become finalized. There is no way for any ramifications to come towards you, regardless of whether it's my class or any other one. And it's completely anonymous. Once it gets sent to me, it gets completely generated. And the responses, it just shows me a response mentioned. It doesn't say who sent it, when they sent it, anything like that. It just says, here are the people that responded to this question. And then there's the multiple choice ones. And those ones just give me a little a distribution of your choices. So does anybody have questions on it? Oh, plenty. Yeah, like you cannot. What I've learned in teaching is that I cannot please everyone 100% of the time. What? What did you say?
They're just.
They are. I'm too cool for school, right? Okay, he's gonna get a haircut. Oh, well, I'm glad. Like, he's got tenure. Like, he's got like ultra tenure though. He's got like tenure upon tenure. His tenure has tenure. Yes. Yes.
Do you get a redo on it?
No. So the final exam is departmental. Like as I said, I don't write it, and it has its own stipulations that come with the course that our team has decided. If maybe they decide there should be a redo, maybe I could do that in the future. But as it stands right now, they don't do that. I'm kind of like the only teacher who does that at CSN. Erica. I believe 20%, if memory serves. Is that a 20 or 25? Because each exam's worth 20, quizzes are worth 20. Yeah, so I think it's 20%. So, any other questions? Otherwise, if I don't see you on Wednesday, have a lovely Thanksgiving. If I do see you on Wednesday, awesome. And there's no quiz on Wednesday. I'm not going to be that guy. All right.
Like actual
material. We probably will go through the fundamental theorem of calculus part 1 question, this one right here, but that's about it. The rest of it will be for review and stuff. All right. See you then.